In the last video, you bound a single data object using UI Builder. Now let's connect that same UI to real data at runtime. We'll make a controller script and recreate the bindings in C#, and then we'll show you a way to simplify the workflow. Before we do that, we've removed the bindings from the previous example. So this is the same UXML, just without any data binding. You can remove the old bindings from the ... menu, and even unset the data source object entirely. We'll rebuild all these same bindings in C#. In part 1, we connected UI elements like the player name and current health label using UI Builder. Once we had bindings and assigned a data object, the UI updated automatically. But that setup was static. The UI always pointed to one scriptable object asset on disk. In a real game, our gameplay data changes. We need a way to assign and swap data at runtime. To accomplish that, we'll use a small controller script that works with the data binding system. Before actually working on this controller, we'll need to update our player data. In part 1, the UI only read from the data. Now we need to modify it at runtime. Current health needs a setter, so here we expose a method to set the value and clamp it so it always stays within range. And now we can change that value at runtime, not just read it. And we also have some helper methods to increment and decrement health. Gameplay systems can then call these to damage or heal the player. We'll use these methods to update the current health property and then test the binding at runtime. We'll manage the data binding with a simple controller script. Here it's a health bar controller. This isn't a presenter, it doesn't push values into the UI. It works with the data binding system. It gets references from the UI document, sets up bindings, and assigns the data source. We'll start by querying the UXML for the elements that we want to bind. Let's just first set up one binding on the current health label. Then we define the binding itself using the set binding syntax, like this. Text is the target property, the first parameter, and then we'll create a new data binding object as the second parameter. So this describes a relationship. When we get a data object, we'll read whatever value is at the current health data path and then assign that to the text property. At this point, nothing happens yet. There's no data source. So we create a runtime instance. In part 1, we use the scriptable object asset directly, but we don't want to modify that at runtime. Instead, we could use a serialized player data as a template. You drag that into the inspector to define initial values, and then create a copy at runtime. This gives us a new instance that we can safely modify. Once we have that, we can assign the data source. Root visual element, data source equals player data. UI Toolkit then resolves all the bindings against that object. Also, for this demo, we'll expose the runtime instance as a property. This lets other scripts modify the data and test the binding. In a real project, it would just come from your gameplay systems or health manager. Right now, we have one active binding. If you save this and then attach it to your health bar game object, just assign the UI document and scriptable object template in the inspector. Since we're working with a runtime instance, we can't edit the original scriptable object directly. We'll use a small tester script to modify the runtime data. And this will simulate how gameplay systems would change the player's health. The tester hooks up the plus and the minus buttons at the bottom. At runtime, this calls increment health and decrement health on the player data instance. We just need to provide a reference to the health bar controller and root visual element ID. In play mode, when we press the buttons, we're modifying the data at runtime, and the UI updates automatically. Remember that we're changing the data, not the UI. The label is bound to the current health of the runtime player data, so it updates on its own. Now we can go back to the controller and add the rest of the bindings in C#. For simple cases, we repeat the same set binding pattern. These properties should look familiar. They match what we set up in UXML in part 1. When we use converter groups, the syntax gets more involved. We create the binding first, keep a reference, apply the actual converter group, and only then call setBinding. Now, this is a perfectly valid way of setting up data bindings and sometimes necessary for creating them at runtime. If we run this, we rebuilt the full health bar data binding in C#. When the health changes, the UI updates correctly, but the issue here is scale. Each element needs its own binding, property path, and sometimes converter setup. Compared to creating those bindings in UXML, this version is more verbose, and it doesn't have the interactive workflow of the UI builder either. So instead, we can use a hybrid approach. UI Toolkit lets you define bindings in UXML, but instead of assigning a specific object, we just set a data source type. Click Select Type, filter by name or namespace, and then choose the Player Data Scriptable object. This tells the UI what kind of data to expect without assigning a real instance yet. Then set up the bindings exactly as we did in part 1. When you create the bindings, select the Type option. So the bindings live in UXML, but they don't resolve until runtime. In UI Builder, you'll notice the binding icon is hollow, and the data doesn't fill in on screen like it did before. The data binding isn't fully resolved yet, and that means that something else, the controller in this case, will provide the actual data at runtime. We would then go through all of the parts of the UI that need bindings, the current health, max health, progress bar, width and color, etc. And you can set up the bindings exactly as before, but this time we would use data source type. All the same properties would be available in the data source path. Apply the same converters if necessary, and once you reapply all the bindings here in UXML, they're fully defined, but still waiting on real data. Nothing is connected yet. That only happens at runtime. Back in the controller, the script becomes much simpler. We no longer create the bindings in C#, those are already defined in UXML, so all of this code can go away. In this hybrid workflow, the bindings can be set up interactively, and the controller just provides the data. At runtime, all it really does is this. It sets the data source of the root to the player data, and that's enough to activate every binding in the UI. The controller script is pretty minimal, and you can extend it with helpers when you need it. For example, you might want a method to swap the data source at runtime. You could do that like this. This hybrid approach splits the responsibility. Bindings are authored in UXML, and the controller supplies the data at runtime. In play mode, we've restored the behavior to the health bar. The UI updates immediately when the health changes and everything works like it did before. This covers 3 approaches to data binding: UXML and UI Builder with static data, the C# API with the controller script, and this hybrid workflow that combines both. All 3 get you the same result, update the data, and the UI stays in sync. So far, our bindings have updated automatically. But as your UI grows, you may want more control over when the bindings refresh and how much work the system does to keep everything in sync. UI Toolkit already checks your data during its update cycle, but we can make that process more efficient with versioning and change tracking. The goal is simple. Do a quick, low-cost check first, and only refresh the UI when something actually changes. We implement this in the data model. So let's open the scriptable object and fold some code out of the way. Then we'll focus on current health since that drives the health bar. First, we add iDataSource view hash provider. This interface requires a getViewHashCode method. We'll back that with a simple version number, mViewVersion, and return it from getViewHashCode. This doesn't immediately update the UI. Instead, it gives the binding system a lightweight version check. On its next binding pass, UI Toolkit compares that value with the previous one. If it changed, the system knows this data source needs to refresh. Next, we add a helper method called publish. We just need something to increment mViewVersion. When the version changes, the binding system can detect that change on the next pass through getViewHashCode. This effectively lets us buffer updates instead of forcing the UI to react to every intermediate change. Now let's apply that to the current health. In the setter, we exit early if the value is the same. If it did change, we update the backing field and then call publish. This gives the data source a new version, so the binding system knows it needs to refresh on the next binding pass. So that's versioning. Now let's make it more precise with iNotify bindable property changed. This adds a property changed event, and we can wrap that in a helper method called notify. Inside current health, we call notify for the changed property, like this: name of current health. And if we use the caller member name attribute, we don't even need to pass the property name manually. That can trim down just to notify. And so now we have two signals. GetView hashcode tells the system that the source has changed, and the property changed event through notify tells it which properties have changed. And together, that means UI Toolkit can detect that a refresh is needed and update only the bindings affected by that change. Also, we want to invoke notify with any properties that actually changed, plus any computed properties that depend on them. So when the current health changes, health percentage and current health progress change as well. Those are computed values, so we notify them here from the current health setter, and those will need the name of method. Once you use this pattern, UI Toolkit no longer just infers changes on its own from these properties. It depends on these signals that you provide. So if the current health changes, you should call notify for the affected properties and then publish to advance the version. Otherwise, that update might not be picked up until something else triggers a UI refresh. And that's how you implement versioning and change tracking. And of course, this only matters for bindings that update at runtime. If a binding is set to toTarget once, it reads the value just once and stops. So for values like player name and max health, you may not need change tracking at all. Note that in a small UI, you may not notice any of these efficiencies, but in a larger, more data-driven interface, this gives you better control over when the UI refreshes. So that's runtime data binding in UI Toolkit. We started by defining bindings in the UI builder, and then connecting real-time data with a lightweight controller, and then finally adding versioning and change tracking so the UI updates more efficiently. Your UI describes what it needs, your data provides it, and the binding system keeps everything in sync. From here, you can build more dynamic UI without manually updating every element. If you want to find out more about UI Toolkit and runtime data binding, be sure to check out the links in the description. Thanks for watching.